Today I will be discussing the mathematical details of 3D cryptography. 3D surfaces, already I have told you that we will be using three different types of surfaces: ellipsoid, spindle, torus and spheroid. So our objective was to create a crypto system which can work as both block cipher and stream cipher, and the mathematical complexity should be very low of that crypto system. It should be of the order of O(n) square. Moreover, it should be able to perform digital signature and digital envelope. So we wanted a crypto system which could be a sort of multi-role crypto system. And the main design goal was to implement a crypto system for multimedia. And some of the applications for multimedia are 3D computer generated imagery and animation, exhibition showreels, infomercials and screensavers, business marketing tools, corporate sales, filming, TV and video production. So encryption is done by the sender's private key in a digital signature. Decryption is done by the public key of the sender in a digital signature. And some of the applications of digital signature are authentication, non-repudiation and integrity. And this same thing can also be applied to video or high definition video, because it is also a part of multimedia. And before that, we will get back to the history of multimedia. As you can see, this is the algorithm RSA was invented in 1977. So before that, we will start with some basic history of public key cryptography. And when it was applied for video, it turned out to be too slow and insecure. Merkel-Hellman-Knapsnack was invented in 1978. It was too insecure for video. McClinchy cryptosystem was invented in 1978. It was immune to attack by Shor's algorithm. Shor's algorithm is the fastest factoring algorithm ever known, and the security of many crypto systems, for example RSA and its derivatives, is dependent on the factorization of prime numbers. So Shor's algorithm was designed to be executed on a quantum computer. Elliptic curve cryptography was invented in the year 1985, but on the other hand, it had a very great advantage, was that we could achieve the same level of security with shorter key lengths. Lattice crypto system was invented in the year 1996, and it was secure against brute force attack. However, it did have its own limitations. Karmashub crypto system was invented in 1998, and the disadvantage was that the ciphertext size was very large as compared to the plain text size. So for that, we needed an extra overhead in the form of compression combined encryption to solve this problem. And not only Karmashub, I'll say that most of the crypto systems have this problem, that the ciphertext size is greater than the plain text size. Torus crypto system was invented in the year 2003, and the advantage was that the key size was reduced. I'm comparing the advantages and disadvantages for popular crypto systems for video. RSA can play multiple roles of block cipher, stream cipher, digital signature, digital envelope. Key size was flexible, block size was flexible. The disadvantage was RSA was that it was insecure, it was slow, it was very old for video. It was invented in 1977. Lattice crypto system was immune to brute force attack, and the disadvantage was that it did not have digital signature. Elliptic curve cryptography had smaller key size, but it was not appropriate for quantum encryption because the hardware for quantum encryption was different. McClinchy crypto system was very good at key management, key generation, and the disadvantage was that it was very insecure against brute force attack. Torus crypto system, so far no major vulnerability has been discovered, but it does not have digital signature, so it does not have authentication. Karmashub crypto system is faster, but the ciphertext size was greater than the plain text size. And there are some rumors that public key cryptography was invented in Britain, but at that time the hardware was not of very advanced type, so that is why any kind of real life experimentation could not be done of that old technology with that old technology. And these are some of the references which I have used, and these are very good references from a good background like IEEE. So if you want, you can use them and you can get more information. So IEEE journals, IEEE magazines were used, and Okay, so this is IEEE transactions. Okay, this is a US patent. It was in 2016. This one is Springer 2017. This one is 2017. Again, this is Springer multimedia tools and applications. And this is a conference reference. This is a US patent 2017. This is Elsevier 2017. So these are the best references which were taken while creating this presentation video. Okay, so a brute force attack using quantum computer on RSA for video. The vulnerabilities of RSA was that it was insecure against a brute force attack by quantum computer using Shor's algorithm. And what is a bit and a qubit? A normal computer has got a bit in the form of 0 and 1. On the other hand, a quantum computer has got 3 states, 0, 1 and the superposition state. If you are comparing 2 to the power n with 3 to the power n, so this is the reason why a quantum computer is more powerful than an ordinary computer. There are some rumors that quantum computers have been secretly invented, but major governments and major multinational corporations are not disclosing this fact. Public key lengths with the year, as you can see in this figure, in the year 1995, the individual public key length was 768 bits. The corporations were using 1280 bits and the governments were using 1536 bits. However, in the year 2015, it increased to 1536 for individual. Corporations were using 2048 bits and the governments were also using 2048 bit key length. Moving ahead. And key size in decimal digits, as you can see in the year 1991, the key size in decimal digits was 100 and the key size in binary was 330. On the other hand, in the year 2012, it increased to key size of 212 in decimal digits and the key size in binary increased to 704. And these were some of the experiments which were done using RSA for encryption. Now this is the advancement which we have made for factorization using Shor's algorithm. As you can see that the number 15 is product of 5 and 3. It was factorized by Shor's algorithm in the year 2001. On the other hand, in the year 2014, with just 4 qubits. Compare that with 2001, we only used 3 qubits in factorization of 15. However, in the year 2014, we used 4 qubits for factorization of 56153. It shows that the improvements in quantum computation have been faster than our expectations. And as you can see here, in the year 1998, 2 qubits were implemented. On the other hand, in the year 2012, 84 qubits were implemented. So the conclusion which I want to tell you is that we have been very, very fast in implementations of qubits, and not just hardware implementation, but how they are used and how they are implemented at the software and at the algorithmic level. The problem identified after the initial analysis of already existing crypto systems was number 1, speed, because elliptic curve cryptography has got the mathematical complexity of O n cube, and RSA is very, very slow, and vulnerability to side channel attacks in the form of acoustic attacks, brute force attack, power analysis attack. And the possible solutions which we have given in the form of 3D cryptography were, first of all, there should be a mechanism by which it should be easier to create and distribute keys, and the bandwidth requirement of the network should be reduced. And these were the 3 solutions which were proposed. The first of all is the ellipsoid. As you can see, this is a 3-dimensional figure of an ellipsoid. It has got the length of A along x-axis, B along y-axis, and C along z-axis. And I'll come to the mathematical part of it. This is how an ellipsoid was created. This is a code in 3-dimensional surfaces. You can see I have taken a cross section of it, I've cut a cross section of it at an angle, and I've rotated this cross section in 3 dimensions. So from there I'll get an ellipsoid. The basic equation of ellipsoid is x square upon a square plus y square upon b square plus z square upon c square is equal to 1. And I'll take the points x0r, yn and zn on the surface of it. And what I'm doing is that first of all I am encrypting it. So for encryption I need a public key and a plain text. The plain text is yn and zn. I'm dividing the plain text into 2 unequal parts. The public keys are yr, br, zr and cr. These public keys are known to the sender, receiver and the eavesdropper. Now the private keys which are used for the decryption are xr and ar. x0r is a temporary variable whose value will change for every block. So at the time of encryption, I'm using an ellipse because a 3D ellipsoid is made up of infinite ellipses. This is the equation of an ellipse. Here you can see that I am I'm calculating nth block of ciphertext, and at the decryption side, the receiver has got the complete equations of the ellipsoid, and it is using the equations of both ellipse and ellipsoid in 3 dimensions and in 2 dimensions. I mean to say that ellipsoid is in 3 dimensions and ellipse is in 2 dimensions. It is using the receiver is using both the equations to decrypt. And this is the implementation of the digital envelope. In a digital envelope, I have got a symmetric session key. It is used for encryption of the plain text, and that symmetric session key is encrypted using the public key of the receiver. It is sent to the network. It is decrypted using the private key of the receiver. And once that symmetric session key is decrypted, the decrypted symmetric session key is used for decryption of the ciphertext and get back the original plain text. So this is the digital signature in ellipsoid based crypto system. As you can see over here, ciphertext is okay. I'm doing modifications of this equation. I'll show you that equation. This modification was done, and after that we performed digital signature on it. This equation like this xr minus x0r upon ar was sent to the right hand side, and this yr minus yn upon br, zr minus zn upon cr, this was kept to the left hand side. So here I am doing digital signature. It is 1 minus x pks public key of the private key of the sender, because digital signature is signed by the private key of the sender and it is verified by the public key of the sender. xps minus x0 pks upon a pks. So this is the private key of the sender, and the ciphertext is XORed with it, and it is multiplied with itself mu number of times because we are performing XOR operation. So for performing XOR operation, the length of both the values should match. Similarly, I am performing verification of digital signature using the public key of sender. As you can see, ypks, zpks, the values of this plain text y and zn, they are same only, they did not change. So again I have done multiplication of itself with mu number of times, and after that I have done XOR because I have to get the original value of alpha back, and I have to match the digital signature. And this is the 3D cryptography using a spindle torus. I will show you the mathematical equations of it. Okay. Now a spindle torus is a 3-dimensional figure which is made up of infinite circles, and this is the basic equation of the spindle torus, which you can see. The equation of a spindle torus is r minus a square plus b square plus this under root plus c square is equal to r square. The public keys which are used for encryption are a and c, and the plain text is divided into 2 equal or unequal parts, p, n and rn. So this is how I've calculated the n block of ciphertext. It is equation of a circle, and at the receiver end this r is the private key and b is the private key. So and capital R is also the private key. So a receiver has got these both equations, and receiver will be able to decrypt the ciphertext. After that I'll come to this spheroid. This is a 3-dimensional figure. As you can see that the length of the spheroid along x-axis is p, along the y-axis is p, and along the z-axis is q. And this is the center ABC. Here I will be using compression combined encryption because this is a triangle which you can see in the figure. So sum of 2 sides of the triangle is greater than the third side. What I'm trying to do is that I am doing compression combined encryption, and I'm using the same concept of 3D and 2D surfaces to do encryption with compression. Thank you.